Okay, so we come to this part where it talks about shapes of molecules. Now, this part is important. Why is it important? Because once we determine the shape of the molecule, okay, from the shape of the molecule, we will be able to determine something called the secondary bonding. Okay, secondary bonding. Now, secondary bonding, this exists only in covalent molecules. All right. So when we talk about ionic compounds, metallic compounds, they only have primary bonding. There is only ionic bonding and there is only metallic bonding. Secondary bonding only exists in covalent substances. At this moment, you may not fully understand this, but as we go on, you will. Okay. So what we're going to do in this part is, and maybe in the next one or two parts, is to determine the shapes of the molecule. To do that, we need to rely on two things. First thing that we need to rely on is called the Lewis structure, which I will teach you how to do. Second one is called the VSEPR theory. Okay, the VSEPR theory, which is called the valence shell electron pair repulsion theory. It's written here somewhere. Here we go. Okay, electron. All right. So it's here. Sorry, valence shell electron pair repulsion theory. VSEPR theory. Okay. So this is important. So these two things will help you to determine the shape of the molecule. Once you know the shape of the molecule, you can predict the type of secondary bonding that it has. So for the first thing, what we're going to do is we are going to learn how to do the Lewis structure. So I'm going to teach you how to do Lewis structures first. Now, the procedure is given here. Okay, draw the Lewis structure and so on. I will show you how this is done. And then it will come to something called the electron geometry. Okay, and there is something called, so this table will become important shortly. And then there is something else called the molecular geometry. Okay, so these two words I will introduce to you later. Electron geometry and molecular geometry. These are two important words that you need to know. Okay, so later you might come back and you might understand everything that is on this table here, but let's start with the basic thing first. Okay, so look at that. Wow, so all of this in here, you will have to memorize all of these things. Okay, so let's do this. Okay, so let's do electron geometry. All right, so let's do Lewis structures. So we're going to do Lewis structure. So that is what I'm going to teach you now. So let's start with something simple. Let's say a molecule like CH4. This molecule is called methane. Okay, methane is a hydrocarbon. All right. So step number one, you need to go and look at the periodic table and identify which group they are from. Okay, like for example, carbon is from group 14 and hydrogen is not in any group, but right, so usually placed under group 1. So step one is to determine the number of valence electrons that each one of them have. So if carbon is in group 14, carbon has 4 valence electrons. Easy, right? And hydrogen has only 1 valence electron. Okay, so to make things simple for you, if you are group 14, you have 4 valence electrons. If you are group 15, you have 5 valence electrons. And if you are group 16, you have 6 valence electron. If you're group 17, you have 7 valence electron. And if you're group 18, you have 8 valence electron. All right. And in the same token, if you're group 13, then you have 3 valence electron. But of course, 3 valence electrons, usually you are a metal. Okay. But in some cases, it will become important. All right. Okay, so let's go back to this again. So now we have identified that carbon has 4 valence electrons and hydrogen has 1 valence electron. So what we're going to do next is we look at this formula which was given to us, and we notice that there are 4 hydrogens and there is only 1 carbon. So what we do is we put carbon we put carbon as the central atom. Center, that means the atom that is going to be in the center. And since there are 4 hydrogens, we are going to distribute these 4 hydrogens around it, like that. Okay. So we try to make it symmetrical as much as we can. All right. Then what we do is we draw a line between the central carbon and the peripheral atoms. Central atom and the peripheral atom. So the word here I used was central atom, and this is called the peripheral atom. So these are the 2 words that I might use, okay? Central atom and peripheral atom. Now each line that you see here represents a pair of electrons, a pair of electrons, okay? Now in the earlier part here, there were 4 hydrogens, so there are times 4 here. If we total this up, we have 8 valence electrons in total. Am I right? So each line represents a pair of electrons. So what does that mean? There are 2 electrons here, there are 2 electrons here, there are 2 electrons here, and there are 2 electrons here, which means that all of these 8 electrons have been used up already. So this is the Lewis structure for methane. Okay, this is the Lewis structure for methane. Okay, let me just do this, just draw it out here for you one more time. So this is a Lewis structure for methane. Now in this Lewis structure, all of the electron pairs are in bonding. They are all bonded to 2 atoms. So these type of electrons, all of these electrons are called bonding electron pairs. Okay, they are called bonding electron pairs. That means bonding or bonded, whichever. Okay, you want to call this bonded also can. Bonded electron pairs. All right. So that's the Lewis structure for methane. Now let's do another one, something similar. I'm doing things which are similar. Okay, let's do ammonia. Okay. Now you will notice that nitrogen is in group 15, so it has 5 valence electrons. Hydrogen has 1 valence electrons only, and there are 3 of them. So if you total this up, you have 8 valence electrons again. All right. So there's a reason why I'm doing this. I'm dealing with 3 molecules which have total 8 valence electrons for starters. Okay, for starters. So what I'm going to do is I'm going to put nitrogen in the center. I'm going to put 1 hydrogen over here. I'm going to put 1 hydrogen over here and 1 hydrogen over here. If you want to put the hydrogen at the top, it is up to you. All right. So that's what I'm going to do. Okay. Then the next step I told you was to draw a line, 1 line, 2 lines, 3 lines. And I also told you each line represents 2 electrons, right? 2 electrons. So this is 2 electrons, this is 2 electrons, and this is 2 electrons. So which means that I have used up 6 valence electrons. Now I'm left with 2 valence electrons. There are balanced 2 more valence electrons. So what I will do is these 2 valence electrons, I will put it onto the central atom here. The central atom, which is nitrogen. Okay, I'll put it on nitrogen. Let me erase this off. Okay. So I'll put it onto the central atom. Now, when I put it on the central atom, I have a option, I can either put it as two dots like that, or I can put it as a line like this. Okay, I can put it as a line like this as well. So it's up to you. What do you prefer? All right. So like I said, okay, you can either put two dots or line. Personally, I prefer this. I prefer a line because it's neater. Okay. Otherwise, you end up with too many dots. Later on, when we do other examples, you'll understand this. So you can leave it as just a line, or you can leave it as a dot. Okay. So back. So again, so earlier I told you this was bonded pairs, right? So I'm just going to abbreviate this for you, BP lah. Okay, bonded pairs. So here, these are all bonded pairs, right? This is all bonded pairs. These are electron pairs which are bonded to two different atoms. So up here, this is something new. We have non-bonded pairs. Okay, non-bonded pairs. That means non-bonded pairs, which are also known as lone pairs. Okay, they're also known as lone pairs. So if you hear me saying non-bonded pairs or you hear the word lone pairs, they are the same thing. Non-bonded pairs and lone pairs, they are the same thing. All right. So in this case, ammonia has one non-bonded pairs and three bonded pairs. Okay, one non-bonded pairs and three bonded pairs. All right. Then let's do one more example here. Maybe I'll add another one. Okay. Oops. I didn't want that. Doesn't matter. Okay. So it's all right. It's all right. We deal with what we have. All right. Here we go. Let's go with water. Water. Okay. So hydrogen. Again, hydrogen is having one valence electron, and there are two of them. Oxygen is group 16. 16 has 6 valence electrons. So total, we have again 8 valence electrons. So you see what I'm doing here? So we are dealing with everybody who has 8 valence electrons, right? So then what we're going to do is we are going to put oxygen in the center, since there are 2 hydrogens and there's only 1 oxygen. Like in this example just now, there were 1 nitrogen and 3 hydrogens. Usually, if you're given a molecule that you're not familiar with or something new, the question will usually guide you and tell you that so and so is the central atom. Okay, so don't worry about that. But in this case, the person who is single, we put it in the center. All right, we put that person in the center, so make things easier. So oxygen goes in the center, and then I'm going to put 1 hydrogen over here, 1 hydrogen over here. I'm going to put a line here, and I'm going to put a line here, right? So you notice now this is our bonded pair. This is a bonded pair. But hold on. This is two pairs of electrons here, 2 electrons here, 2 electrons here. So total 4 electrons, which means that I still have another 4 more electrons to go. So where do I put this electron? So what I'm going to do is I'm going to put these 2 electrons on the central atom. So I can do it like this, or I can do it like this. So the choice is yours. How do you want to do it? You want to put it as 2 dots above oxygen and 2 dots below oxygen, or a line. It's totally up to you. So in this example now, you have, this is the non-bonded pairs. This is another non-bonded pairs. So which means that in the case of water, you have 2 bonded pairs versus 2 non-bonded pairs. In the case of ammonia, you have 3 bonded pairs versus 1 non-bonded pair. And in this case of methane, there are only 4 bonded pairs. Okay, so you see what has happened? From 4 bonded pairs, it became 3, and 1 became a rebel, became a non-bonded pair. And here it became 2 bonded pairs and 2 non-bonded pairs. So this will affect the shape of the molecule. How the molecule ends up looking is affected by this. Okay. So the first thing I want to do with you here is, I want to explain to you what's the difference between the word electron, oops, can't perhaps spell that word. Here we go. Electron geometry. Okay, so what is electron geometry? So when we do electron geometry, right, what we do is we assume all electron pairs around the central atom to be non-bonded pairs or lone pairs. We assume that. You can also assume that they are all bonded pairs. Up to you. Okay, up to you. You can assume they're all bonded pairs, or you can assume them all to be non-bonded pairs. So, for example, like in the case of methane just now, right? Okay, so methane. So what I'm going to do is I'm going to assume that all of these are non-bonded pairs. So I'm just going to put lines. See, at the end of the line, there's nobody waiting, right? This is just so carbon has 4 lone pairs. So now we come to methane. If you look at methane just now, there was one hydrogen here, there was one hydrogen here, there was one hydrogen here, and this was a lone pair, correct? So what I'm going to do is I'm going to assume that, hey, all of them are lone pairs. Okay, all of them are lone pairs. And then in the case of water, I had one line up here, one line up here, and this was water. This was hydrogen. So what I'm going to do is I'm going to assume, hey, everything here is a lone pair. So you notice that in this example that I've just done with you, all of these guys, all of them have 4 non-bonded pairs. Okay, they all have 4 non-bonded pairs. If you look at the electron geometry, for their electron geometry, they all have 4 non-bonded pairs. Okay, so if we look back at the notes here, right? If we look back at the notes here, let's come back here again. Okay. At the beginning here. Here. Okay, here. You see, electron geometry, right? Number of electron pairs. Okay, number of electron pairs 4. So 4 number of electron pairs. Okay, the shape is called tetrahedral. So which means that the electron pairs will arrange themselves in this way. Tetrahedral. And the angle, let's do this. The angle here is 109. Excuse me, 109.5. The angle here is 109.5. Every angle here is 109.5. That's what it means. Okay, so in the case of water, ammonia, and methane, their electron geometry is tetrahedral. Okay, they all started off looking the same. Okay, they all started off looking the same. Then what happened is they started having different numbers of bonding pairs and non-bonding pairs. So if we come back down here, there's another table here. Okay, here we go. All right. So you see in this table here, if you had 4 bonding pairs, like in the case of methane, okay, in the case of methane, if you remember, it has 4 bonding pairs and it had there was no lone pair. The shape remains as tetrahedral. Okay, so the electron pair arrangement, so this is electron geometry. Okay, sorry, let me change color. This is electron geometry. Okay, erase. Okay, this is electron geometry. Electron geometry is tetrahedral. Okay, then what happens is the shape of the molecule remains as molecular shape. So this is molecular geometry. Molecular geometry remains as tetrahedral because it had 4 lone pairs. Now it has 4 bonding pairs. It's exactly the same. Okay, so the angles, everything remain the same. So the angles in methane, all of these angles, everything remains the same as 109.5 because they are the same. But when we came to methane, if you remember methane just now, methane had 3 bonded pairs, okay, and 1 lone pair. Okay, so this is lone pair. So the shape of the molecule is called trigonal pyramidal. And this is the lone pair. This is a lone pair just now. So this, imagine this is the nitrogen. Change color again. Change color. Okay, let's use white. This is nitrogen. This is one hydrogen here, this is another hydrogen here, this is another hydrogen here, and remember this was a lone pair, right? Now what happens is this angle here becomes 107. When I learned it, it was 107, but now it says it's 107.5. Should you memorize these angles? I think for these basic guys, yeah, you should. It'd be a good idea. So the angles between the hydrogens, so if I could draw an angle from this hydrogen to this hydrogen, it will also be 107.5. But, okay, let's erase this again. But what happens is, the angle between the lone pair and this bonded pair, or the lone pair and this bonded pair, or this lone pair and this bonded pair, this angle is greater than 107.5. Now, earlier you see in tetrahedral, every angle was the same, 109.5. Now we have two sets of angles. One is 107.5 and the other one is bigger than 107.5. I don't know what it is, and it does not matter to anybody what it is, but it's not the same. So when this happens, we say this molecule is non-symmetrical. It's no longer symmetrical. That means you have two sets of angles. It's not symmetrical anymore. All right. And the shape is called trigonal pyramidal. It's no longer tetrahedral. So if you could see an ammonia molecule with your naked eyes, this is how it will look. It will just look like that. All right. It's not flat. It's not flat on the floor. It's a bit lifted, and then that's the angles that you see, 107.5. Okay. Now let's look at the last molecule that we did just now, water. If you remember water, okay. So water. What did I do just now? Water was like this. 1, 1, and then 1, 1, correct? So it has 2 and 2. So that means it has what? Okay, number of bonding pairs 2, number of lone pairs 2. This shape is called bent. Okay, it's called bent. So you see, bent shape, this angle here is now 104.5. It started off at 109, then it dropped to 107. Now it's dropping even more to 104. So the bonded pairs are getting closer together. The bonded pairs are getting closer together. Okay, they're getting closer together. And so then this angle between the lone pair and the bonded pair is going to be different. All right, and so let's call this A degrees. Okay, let's say we call this A degrees, and this angle between the bonded pairs, the lone pair and the lone pair, we call this, let's say, B degrees. Okay, so which means that you have three sets of angles in this molecule. So this molecule becomes bent. Okay, this is also non-symmetrical, and it becomes bent. So if you look at it, sometimes we call this a V shape. Okay, water is like this. So we call it V shape, or we call it bent. All of this happened because you suddenly have bonded pairs and non-bonded pairs. Okay, so before we end, I just want to explain last part. I want to tell you what was the VSEPR, valence shell electron pair repulsion theory, all about. You see, now if you imagine all of them are having the same type of bonding. Okay, let's say this was carbon, this was hydrogen, this was hydrogen, this was hydrogen, this was hydrogen. So the repulsion between this and this electron pair 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 and this, every electron pair, the repulsion is the same because they are all identical. They are the same person. They're all bonded pairs. So the degree of repulsion that they will have is going to be exactly the same. That is why they all work amicably. That means they all work together very well and said, okay guys, we are all going to be as far away from each other as possible, which is 109.5. When you come to ammonia, these three guys here, okay, so this is ammonia, right? Okay, so this is hydrogen, this is hydrogen, and this is hydrogen. So these three guys at the bottom there, they're all bonded pairs. They're all bonded pairs. That means it's between nitrogen and hydrogen. So their degree of repulsion is going to be the same. The electrons here are going to be repelling each other identically because they are the same person. But now we have a lone pair. This lone pair is different because it's a lone pair. We don't have another atom at the side here to stabilize it. We don't have, all right? We don't have that atom. So what is going to happen is this guy is going to exert greater degree of repulsion on the bonded pairs. So it's going to exert a greater degree of repulsion on the bonded pairs. So it's going to demand for greater space. That is why it takes up a greater space, and the bonded pairs become a little bit closer to each other. So from 109, it becomes 107. And finally, in the case of water, right, these two guys are bonded pairs. So they have repulsion among themselves. But you see, the lone pairs also have repulsion among themselves. They also hate each other. They will also repel each other. And in that process, they also repel the bonded pairs. So there is so much of repulsion going on. There's so much of hate going on here. First, the lone pairs hate themselves. They hate themselves. They push each other. Push. And then the lone pair hates the bonded pair. Push. And the bonded pair and bonded pairs push each other. Push. Everybody's pushing each other. And that is why the shape of the molecule becomes bent. It becomes from 109, it drops to 104. Okay. So this repulsion, the repulsion that exists between the electron pairs around the central atom, is called the valence shell electron pair repulsion theory. And because of this degree of repulsions, the molecules end up adopting a different shape to minimize the repulsion. Okay, I repeat, because of VSEPR, because of valence electron pair repulsion theory, the molecule adopts a shape which has the most minimum amount of repulsion, right? So either it becomes tetrahedral, or becomes bent, or it becomes octahedral, or it becomes trigonal, bipyramidal. There's so many different shapes that you'll come across. So that's what happens. Okay, so we'll stop here. In the next video, we'll look at other molecules and we'll try to predict their shapes.